Hi, this is the second of two modules on pre-processing. In the first module, we talked a little bit about slice time correction, motion correction, and co-registration. In this module, we'll turn our attention to normalization and a little bit of spatial smoothing. So here's the pre-processing pipeline that we discussed last time. So again, pre-processing is performed both on the fMRI data and on structural scans that are collected prior to the experiment. And so last time we talked about taking the functional images and denoising them, so looking for spike artifacts, performing slice time correction, and also motion correction. We also talked about taking the structural imaging and co-registering it to the functional, so mapping them onto each other. So at this point what we have is we have a structural image which is living in the same space as the functional images, so they're aligned perfectly with each other. So in this module we're going to now look at aligning these structural and functional images to a standard atlas space, so we can compare between different subjects. We'll also talk about smoothing. So normalization is very important in fMRI because it's clearly all brains are very different from each other. The brain size of two subjects can differ in size up to 30%. Also, there can be substantial variation in the shape of the brain and what they look like. And so comparing two different brains from two different subjects, it can be very, very difficult. So what normalization does, it allows one to stretch, squeeze, and warp everyone's brain so that it's placed onto the same coordinate system as some standard brain. The structural MR images used in the co-registration procedure is the one that we warp onto this template image. So what we have is we have a T1 template, which is the kind of the target image that we have in this procedure. And then we have a high-resolution T1 image, which has been co-registered to the functional images. So that's the individual scan. So what we want to do is take this high-resolution T1 image and map it onto the template image. And so what we do is once we've done that, we get a normalized T1 image in standard space. So what we do in that case is we have a set of transformations of the high-resolutional T1 image onto this standard space, and which we can later apply to all the functional images. So what are the benefits of normalization? Well, for one, spatial locations can be reported and interpreted in a consistent manner. So if I perform a study and I have activation in a certain area, I can report the coordinates of that activation and it will be meaningful to other researchers. Second, the results can be generalized to a larger population because, again, we're able to compare brains because we have everyone's brain is on the same coordinate system. Results can be compared across studies. Since our analysis are performed on the same coordinate system across studies, we can compare whether or not the activation in your study is at the same location as in my study. And then finally, results can be averaged across subjects. And so in this case, we can consistently use multiple subjects' data in a way that's meaningful because everyone's voxels are defined to be in the same areas of the brain. Well, what are the cons with doing normalization? Well, one is that it reduces spatial resolution, and the second is that it potentially introduces errors because we have to interpolate the brain and there's errors in warping and whatnot. So what are the target images used when performing normalization? Well, the classic one is what's called the Talairach space. And this is based on the brain from a single subject. It was the cadaver of a 60-year-old French female. And it's based on a single hemisphere of her brain. And in the Talairach coordinate system, the origin is set at the anterior commissure. And it's oriented so that a line joining the anterior and the posterior commissure is horizontal. So that's how the coordinate system is defined in the Talairach space. Lately, people are becoming more enthusiastic about using what's called the MNI brain. So this is the Montreal Neurological Institute. So this is the combination of many MRI scans on normal controls. So in the current standard, there's 152 normal controls. And they were all right-handed. And so in general, because we're combining scans across many, many people, this would tend to be more representative of the population, the MNI brain, than, for example, the Talairach brain, which was just based on a single individual. So how is normalization performed? Well, there are a lot of different ways of doing that. The classic approach is what's called the landmark-based methods. Here you align certain anatomical features in the different brains and try to match them up to each other. This is the approach that Talairach originally took. The most common approach is what's called volume-based registration. And so here we're basically just trying to overlap the brain volumes onto each other in an efficient manner. And this is kind of similar to what we were doing with co-registration beforehand. Here you typically use maybe kind of an affine transformation or alternatively nonlinear transformations to do volume-based registration. There are also computational anatomy approaches, and so here you do diffeomorphic transformation. These are very mathematically rigorous types of methods, and they're currently beyond the scope of this class. Finally, there's surface-based methods where we work on cortical surfaces. So basically, you try to map up two cortical surfaces with each other. After we've normalized, the next thing that we often do in pre-processing is spatial smoothing. So in fMRI, it's very common to spatially smooth the acquired data before performing statistical analysis. There are a variety of reasons for doing this. One could be to increase the signal-to-noise ratio, the other would be to validate distributional assumptions, and the third could be to remove certain artifacts. So what's spatial smoothing about? Well, we take a brain like the one here on the left, and then we apply a Gaussian kernel to it, which basically averages locally brain voxels with one another under the kernel. And so we would get a brain that looks like the one to the right here, kind of a blurrier brain. So why would we sacrifice this fine spatial resolution to get a blurrier image? Well, there are certain benefits with spatial smoothing. One is that it can overcome limitations in the normalization by blurring any residual anatomical differences. So basically, what we mean here is that the normalization procedure that we just performed is can be imprecise and can have artifacts in certain areas. Sometimes we want to smooth over those rough edges, and smoothing can help us do that. The second benefit is that it could increase the signal-to-noise ratio, or the SNR. So basically, if you have multiple voxels that have the same signal, then it's optimal to average over them because we retain the signal but decrease the noise by averaging. So if we retain the signal and decrease the noise, we increase the signal-to-noise ratio, and that makes it easier to detect activation in those regions. The third reason is that it may increase the validity of statistical analysis. We often assume that the data is normally distributed, and that's more likely to be true if we're averaging over multiple voxels. Fourth, it's required for Gaussian random field theories, and so we haven't talked about that so far, but when we talk about multiple comparisons later on, we often use Gaussian random field theorems to perform these types of analysis, and they require a certain amount of smoothness in the image. Well, what are the cons with performing spatial filtering? Well, the obvious one is that the image resolution is reduced. So instead of having very, very small voxels, we kind of increase the effective voxel size in the image. So again, spatial smoothing is performed by applying a Gaussian kernel and just moving it across the brain. And the size of the kernel is determined by something called the full width at half maximum, or the FWHM. And this measures the width of the kernel at 50% of its peak value. So whenever talking about Gaussians, as a statistician, I often think about it more in terms of the standard deviation, and so there is a one-to-one relationship between the full width half maximum and the standard deviation. And so the full width half maximum is usually measured in terms of millimeter. So how many millimeter smoothing do you perform? Typical values can range from, say, 4 to 12 millimeter. Now, the matched filter theorem states that a filter that's matched to the signal will give optimal signal-to-noise ratio. So what that means is that, let's say that we have activation in 5 regions that are next to each other. Well, according to the matched filter theorem, it's optimal to average over those 5 regions because we retain the same signal but decrease the noise. So it can be very useful to smooth the data if you're smoothing in a manner that's living up to the matched filter theorem, that's kind of smoothing over regions that are coherent. However, typically the amount of smoothing is chosen beforehand and independently of the data. So we're not really using the match filter theorem. We're basically applying the same amount of smoothing throughout the whole image. And so even though that could be appropriate in some regions of the brain, it might not be appropriate in others. Well, what are solutions to this? Well, adaptive smoothing could be an option. There's some work on using non-stationary spatial Gaussian Markov random field models to do smoothing instead. Or you can do smoothing that varies across space and time. And so methods exist for doing that, but they're not kind of mainstream methods. The most mainstream is just to do Gaussian smoothing using a fixed kernel. Okay, so now we've discussed the entire pre-processing pipeline. So to recap, we have the structural images co-registered to a functional image and thereafter warped to an atlas template. The functional images are denoised, slice time corrected, and motion corrected. Thereafter, you take the warping parameters that you obtained from warping the structural image to the atlas templates and apply them to the functional images, so they are also warped onto the atlas space. Thereafter, you perform spatial smoothing, and you're then ready for analysis. Now, mind you, there are lots of different ways of performing pre-processing. This is just one potential pipeline. Some people, do it in different orders, and some people don't do certain parts of this or do additional parts. So there's basically as many pre-processing pipelines as there are studies, and this is just an example of one possible pre-processing pipeline. Okay, so that's the end of this second module on pre-processing. Now that we've learned how to pre-process our data, we're ready for statistical analysis. So that's going to be the meat of the class and the focus of the remaining modules. Okay, I'll see you then.